Okay, let's talk first about regions in a circle. Firstly, ignore that little dot there. That's the centre of the circle created by my little program. Forget about that, it's not relevant. What I'm interested in is this. There's a dot there and a dot there, and if I join those two dots, I've got one line and I've created how many regions? Most people could probably work out 1, 2. In fact, I could number them like that. Great. And just for fun, what if I had no dots here? I just had a circle. How many regions would it have? 1. Awesome work. What if I do 3 dots? And I have 3 lines joining, so I want to join each dot, which is on the outside here, to each other dot. So I want to join that to that one and that to that one, and the same with the others. Well, in this case, that automatically happens. How many regions now? 1, 2, 3, 4. I told you to ignore that dot. Keep ignoring it. So 2 dots gives me 2 regions. 3 dots gives me 4 regions. Let's keep going. What if I put 4 dots on? 1, 2, 3, 4. How many regions do I have now? 1, 2, 3, 4, 5, 6, 7, 8. Let's do a recap here. I had 2 regions, then 4 regions, now 8 regions. Okay, put that aside. What if I have 5 dots? There's my 5 dots on the outside there, and I want to join each line to each other dot. In other words, if I start with this dot here, I want to say that's got to join to every other dot that it can join to. And I want to do that for each of the dots. Again, ignore that one. How many regions do I have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Man, I love maths, it's just full of patterns. 2, 4, 8, 16. So I can fairly confidently predict that with 6 dots it's going to be 32. Let's go and do that just to verify it. Okay, so I've got 6 dots on the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 14, 15, I bet you're thrilled that I can write numbers. There's a little region in there, that's actually 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, what? That's it, 31 dots. Well, 31 regions, I should say. That's exactly right. So it goes 2, 4, 8, 16, 31. Did I do something wrong? No. In fact, if you want to go and try it with 7 regions, you'll find that 7 dots, the correct number of regions for that is 57. There you go. Maths is all about patterns. What's next? Let's talk about Mobius strips. Alright, first thing, please forgive the purple glue. That's from my daughter. Now, if we take a strip of paper like this, just an ordinary strip of paper, and glue it like that, that's called a strip of paper which is glued. If we give it a twist like this, so let's hold it like this, give it a twist around and then glue it, just like that, glue that together nicely. It may be purple but it still works. What we have now is a Mobius strip, and Mobius has got that funny little 2 dots on one of the letters, so it's probably pronounced differently. This only has one side, and so if I was to take a pen and draw along this side and keep going, obviously not connecting it, but you can see it's going to keep doing this. Where will we get? We'll keep going around here, along this way, my drawing skills are exquisite, as you can see. But as you can also see, that's actually come back to where I started. So a Mobius strip has one side. These things are actually used in plants, like machinery plants, because they can get more than the normal wear out of a piece of rubber or something when they're making stuff. Practical application? Maybe so. Now, that's all very good and well, but these do really cool things as well. Okay, well I've got here a Mobius strip where a normal Mobius strip, and I've just cut down the centre. I've made a single cut going right down the centre. I've done it all. I'm just about to get to the end here. Let's see what happens when I do that. Just continue the cut until it does that. What have I got? Ah, that's interesting. That's created another Mobius strip. This time has it got a couple of twists. In fact, it does. It's made one long Mobius strip with 2 twists in it. Let's keep going. Alright, well this time I've taken a Mobius strip and I've cut it down in thirds. So instead of cutting it halfway, I've cut it in a third. I've started at one end and I've kept working my way around. I'm just getting back to the end now. What have I got this time? My goodness, I've got 2 Mobius strips intertwined. One weird one, one shorter one. Let's keep going. Alright, this here one, I've got a normal Mobius strip, but I've twisted it twice. Given it 2 twists and I've cut down the middle. What do we get? Oh, I've got no idea. A couple of intertwined bands. One looks like it has 1 twist, maybe one has 2. Who can tell? Okay, so what I've got here is 2 circular bands this time, not Mobius bands, and they're just pasted one on top of the other in a perpendicular manner. Let's see what happens when I cut these down the centre of each circle. Alright, I've done most of the cutting. Let's get to the end and see what happens. I'll just break that through to that part, and I'll just break this through to this part here. Now what do we have? Oh, we haven't quite cut it. Got to cut that there. Of course, we have a square picture frame. That's bizarre. Well, this time I'm doing the same thing, but instead of circular bands, I've got Mobius strips. So I've got one Mobius strip pasted perpendicularly onto the other one. Let's cut through the centre and see what happens there. Just coming to the end now. It looks like a bit of a mess. Let's see what we've got. We've cut that one there, and we've got one more to cut here. What do we get? Oh yes, of course, we get 2 intertwined hearts. Of course we do. And now I want to play something called the chaos game. And the chaos game basically says, start with a reasonably equilateral triangle, that sort of thing, 3 points here. And I'm then going to start with a seed point. And my seed point can be anywhere inside the triangle. So I might say my seed point is there, for an example. And now I would choose, I might do this rolling a dice, or just choose some random numbers here. And out of random numbers 1, 2 and 3, if I choose the number 1, then I want to move halfway between the seed point and that dot. If I choose the number 2, I'll move halfway between the seed point and that dot. If I choose the number 3, I'll move halfway between the seed point and that dot. So let's go randomise stuff. It's 2. Okay, so I go halfway between here. That, halfway between there and there, becomes the new seed point. And then I repeat. So the next time I choose the number 1, randomly. So now I've got to go halfway between here and here. So I'll put it about there. The next time I'll choose the number 2. So I go halfway between here and here. And I'll put it about there. The next time, the number 3. So now it's halfway between those 2, so it's about there. Now this is looking rather random. What would happen if I did it with a few more? Well, you'll be happy to know that I've done this on an Excel spreadsheet. Let's have a look at it now. Well, here you can see that I've done it with a few points, and I've got certain random numbers. If I press refresh, it creates different random numbers and puts different points on there. Let's do it again. There we go. Now, this is only with the first 6 points. What happens if I just keep doing it? And I'm just going to change here the actual number of rows that I've used. You can see I've only used up to row 10. So I'm going to use up to row 65,000. I'm going to do basically 65,000-ish of these things and see what happens. Ah, yes, of course, the Sierpinski Triangle. Why wouldn't I have thought of that? But you might say, wait a minute, what if your seed point was changed? So instead of having it at 50-50, I'm going to change this to 23, I don't know, 87. What happens now? Ah, you can see a few different points there, but essentially it's the exact same thing. What happens if my seed point is outside that triangle? Here's 0 to 100 and 0 to 100 on the horizontal and vertical axes. Well, what if I make my seed point at, I don't know, 134, then 456? What happens then? Guess what? You get exactly the same thing with a few weird different points in here. So it depends on your seed point, but it's still going to do that. Now, speaking of triangles, let's talk about Pascal's triangle. Blaise Pascal was a French man. He's now dead. But he did a lot of stuff with philosophy and mathematics. I think it might have been him who said, "I think, therefore I am." I think it's a pretty famous quote. And he came up with this triangle, and it's called Pascal's triangle for obvious reasons. It's a very, very simple thing to do. You can see how I'm doing it. Just start with a 1 and a 1, 1, and then add each of those numbers to get the next one down. It's quite a well-known thing. I could keep going here, but I've run out of room to do the 1, 8 row. That's Pascal's triangle. What can we find in Pascal's triangle? Using this one, which I've already got pre-drawn, is the triangular numbers. There they are. Triangular numbers are numbers that you can make triangles out of. For instance, 1 is the first one, but I can also go 1, 2, 3 and make a triangular number. I can also extend that and make 1, 2, 3, 4, 5, 6, and that's the next triangular number. So we've found the triangular numbers. What else can we find? What about the powers of 2? Where are the powers of 2? Well, what if we go and add all of these things? What do we get? That's 1, that's 2, that's 4, that's 8. You never guess what the next one is. 1 plus 4 is 5 plus 6 is 11 plus 4 is 15 plus 1 equals 16. There's the powers of 2. That's 2 to the power 4, it's 2 to the power 3, 2 squared, 2 to the power 1, and 2 to the power 0. So the powers of 2 are contained all the way down here. 2, that's too easy. What about the powers of 11? Okay, what about this? 1, look at the numbers formed by the row. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Go ahead and verify yourself, but that is 11 to the power 0, 11 to the power 1, 11 to the power 2, 11 to the power 3, 11 to the power 4, and it actually keeps going. Even though 15101051 is not in itself a power of 11, if we do something like, I believe from memory, I need to go 1, then I add the next two numbers, 5 and 1 makes 6, then I add the next two, 0 plus 1 makes 1, and then I do the last three numbers, 0, 5, 1. That is in fact 11 to the power 5. I don't have my calculator with me, but I'm pretty confident that it is, and you can keep doing that. Okay, what about the Sierpinski Triangle? We've already seen it. Let's see it again from Pascal's Triangle. All we have to do is shade all of the odd numbers, and that's what I've done here, and you can see we've got the Sierpinski Triangle. What's next? The prime numbers. Well, if the second, this is the first number in each row, if the second number is prime, all the other numbers in that row are divisible by that prime number. We're of course not counting about the ones. So for instance, there's a prime number, well that's the only other number in that row, but here's a 3, so that's a prime, so then every other number that's not the 1 is divisible by 3. Yep, that's certainly true. What about this? 5? Yes, we've got 10 is also divisible by 5. The next one is 7. 21's a multiple of 7. 35's a multiple of 7. I haven't shown you here 11, but you can go verify yourself that it's true for that, and it's true for all prime numbers in Pascal's triangle. But it gets better. What about the points on a circle? Points on a circle? Yeah, that's right. Remember that points on a circle thing I did right at the start? And it created a number of regions. Well, what happens if I think about that? There's the first one. Here is the second one. This is what I'm talking about. And let's consider it. Points. How many points did this one have? 2. How many points did this one have? 3. The next one had 4. The next one had 5. Well, after that, I want to think about the number of segments that are in the regions, or in the circle. So in this first one, there's actually one segment. That's a line segment there, so that's a 1. In the second one, there's 1, 2, 3 segments. What about the 4, or the one with 4 dots? Let's just make that quickly. How many segments did we have? 4 around there and another 2, that makes 6. Okay, the next one with 5, the number of segments was 10, and you can go verify that for yourself later. What about the number of triangles in each of these things? Triangles. Okay, well how many triangles are in this one? None, so we can leave that blank. How many in this one? 1. How many in this one? 1, 2, 3, 4. 4 triangles in this one. Okay, what about the next one? Well, there's actually, if you go and draw it and have a look at it, there'll be 10 triangles. What's next? What about the number of quadrilaterals? Number of quadrilaterals, none in this one, none in this one. How many in this one? Just the one quadrilateral. How many in the next one? Well, I can tell you that there would actually be 5 quadrilaterals. What about the number of pentagons? So 5-sided figures, none in this, this, this. In the 5 version, there will be 1 pentagon. In the next one, there are actually 6 pentagons. And I don't know if you've seen it yet, but here it is. Here's Pascal's triangle. I'm going to stick a 1 in front of every one of these rows, and there you've got 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And the next one will be 1, 6, 15, 20, 15, 6, 1. There's circle regions in Pascal's triangle. And of course, I couldn't leave this without talking about the Fibonacci numbers. You're kidding me. The Fibonacci numbers are in Pascal's triangle? Of course they are. Let's have a look. Let's sum the shallow diagonals. So I'm going to do this. 1, 1, 2. Let's sum the next one. 1 and the 2 there makes 3. The next one I'm going to sum 1, 3, 1. That makes 5. Then I'm going to sum 1, 4, 3. That makes 8. I keep doing that. I'm going to get 1, 1, 2, 5. Sorry, 1, 1, 2, 3, 5, 8, 13, etc. And you can verify that the Fibonacci numbers are sitting in Pascal's triangle. Now that leads me on to Fibonacci. It's probably one of the most well-known sequences around, and you get it by starting with a 1 and a 1, and then you add those two numbers to get the next one. So the next one's 2. Then I add 2 and 1 to get 3. Then I add 3 and 2 to get 5. Then 5 and 3 to get 8. 13. 21. 34. What's next? 55. 89. And that just keeps going on forever. That's the Fibonacci sequence. Well, there's a few weird things. In fact, there's a multitude of weird things about the Fibonacci sequence. In fact, there's so many weird things that they've actually got journals just devoted to finding new things about the Fibonacci sequence, and they keep publishing them, so they keep finding new things. But what I find interesting is this number, 89. That's one of the Fibonacci numbers, but in fact, what happens when I go 1 divided by 89, or the fraction 1/89th? It's the same thing, of course. What would the decimal representation of that be? Well, let's have a look at that. Well, 1 divided by 89, if we were to do it on our calculator, would tell us that it is 0.01123595506, and it keeps going, but that's where my calculator runs out. You might say, what's that got to do with Fibonacci? I can sort of see it in the first few digits there, but not so sure. Well, let's write this number out in a slightly different way. Let's go 0.01 plus 0.001 plus 0.0002, 0.0, oh, I keep repeating, you can see the 3's coming down on the next place there. Then I'll put a 5 on the next place. And I'm going to put that many zeros and an 8 on the... How many zeros is that? 1, 2, 3, 4, 5, 6 zeros after the decimal place. Now I'm in trouble. What do I do now? 1, 2, 3, 4, 5, 6. Now instead of putting a 7th zero here, I've gone 1, 1, 2, 3, 5, 8. I'm going to put the 1 of the 13 underneath the 8. And the 3 there. I'm going to keep doing the same thing. I'm going to get the right number of zeros here. 0. Next one is 21, so I'm going to put the 2 underneath there, and then 1. And if I kept doing that, look what happens. 0.01, 1, 2, 3, 5, 9, 5, 5, 9, 5. And you can keep doing that, and if we continue that, it will actually equal this number in decimal form, 1 divided by 89. So there's the Fibonacci sequence in 1/89th, and 89 is itself a Fibonacci number. Now that's bizarre. But what gets more interesting is when I start looking at the ratio of terms of the Fibonacci sequence. For instance, if I take this number divided by this number, 1 divided by 1, that's normally 1. 2 divided by 1, that's normally 2. 3 divided by 2, that's 1.5. 5 divided by 3, 1.6. 8 divided by 5, in fact 5 divided by 3 is 1.6 recurring, 1.66666 keeps going forever. 8 divided by 5 is 1 3/5, which is 1.6 exactly. 13 divided by 8, I don't know what the heck that is, 1.6 something. Now what happens, you can see it's starting to settle down to 1.6. What it actually settles down to is this number 1.61 blah blah blah. I can never remember the rest, but it's called the golden ratio, and it's given that symbol. Now once again, I've done a bit of an Excel spreadsheet, and you can see here I've put the Fibonacci sequence on the left, and on the right I've got the ratio of the terms. And so that next number was actually 1.625, then it goes 1.615385, and it keeps going. And you can see that it settles down quite quickly to 1.618034, but it hasn't actually settled down to that. It's just that's how many decimal places we've rounded to there, but it keeps going. But this thing called the golden ratio is this ratio. It happens to be the ratio of the Fibonacci terms, but that's not actually how it's come about. Before I talk about that, I want to talk about what would happen if I changed the first two Fibonacci numbers. Instead of 1, 1, what about if I put 23, 57? Well, look at that. The ratio eventually, in fact quite quickly, settles down to exactly the same number. What if I changed it to 345 and then 1789? Once again, it starts off differently, but it settles down to the golden ratio. So the numbers that you start with have no difference. It'll always become the golden ratio. Well, the golden ratio is this weird and wonderful thing, and you might have seen it used in certain architectural drawings, and it apparently appears a lot of places. And it's such that we could write it like this: x plus 1 over x equals x over 1. It's the number x such that that ratio is true. In other words, if I start with, and I say, look, I reckon it's going to be roughly there, and that's x, and this here is what I'm calling x plus 1, then if it's true that the ratio of that to that is the same as that, then I've got myself the golden ratio. Whatever that number x is the golden ratio. Well, we can find the golden ratio by solving this equation. And to solve that equation, I'm just going to cross multiply here. X plus 1 equals x squared. I'm going to get x squared minus x minus 1 equals 0. I'm going to solve that using the quadratic formula. A very, very useful thing indeed. X will equal, you all know this, minus b, so that's 1, plus or minus the square root of b squared, take 4ac, so that's the square root of 1, take 4 times 1 times minus 1. Good, I'm glad you all got that. Over 2. Let me go and simplify that. 1 plus or minus root 5 on 2. Now the golden ratio happens to be the positive version of that. So it is 1 plus root 5 all divided by 2. There's your golden ratio. You can tell that to your friends. It's a pretty neat party trick. Now the golden ratio has bizarre qualities and things, as I've said before. We can actually find out a formula for the square of the golden ratio. Would you believe? Let's do that now. Remember back here and we had x plus 1 equals x squared. Well, remember that x is the golden ratio. So that means now I can write that the golden ratio squared is the golden ratio plus 1. That's just a fact. Can't deny it. Well, that means if that's true, what would the golden ratio cubed be? Well, that would be the golden ratio times the golden ratio squared. That's a little 2 there. That would be the golden ratio times golden ratio squared is golden ratio plus 1. And so it's golden ratio squared plus golden ratio. What the heck am I talking about? Well, I'm trying to find the golden ratio cubed. But remember, the golden ratio squared here is golden ratio plus 1. So that's golden ratio plus 1 plus golden ratio. That's 2 golden ratios plus 1. That's an expression for the golden ratio cubed. Now, if you repeat that kind of process, this is what you can get to. The golden ratio to the power 4 ends up being 3 golden ratios plus 2. What about the golden ratio to the power 5? Golden ratio to the power 5 ends up being 5 golden ratios plus, are you kidding me? 5 golden ratios plus 3. Oh my goodness, there's the Fibonacci sequence back again. 1, 2, 3, 5. What's the next one going to be? 8 golden ratios plus 5. You can verify that for yourself. It's left as an exercise to the reader. Now, talking about mathematics, I must of course talk about pi. Every school child knows that pi has something to do with a circle. They're just not quite sure what. Well, it happens to be that the circumference of a circle is pi multiplied by its diameter. Therefore, that means that pi is the circumference divided by the diameter of any circle. So if I was to measure that and divide it by that, I would get pi. How do they work that out? Do they actually draw circles and measure these things? What about the degree of accuracy? No, they don't. Have you ever wondered that? How they know the value of pi? I'm about to kind of show you. But the most bizarre thing I've ever heard about pi is this. And I've got it here from an article by Hans Henrik Stolum, River Meandering as a Self-Organisation Process. It's an exciting title, I know. Simulations of freely meandering rivers and empirical data show that the meandering process self-organises the river morphology or planform into a critical state characterised by fractal geometry. The meandering process oscillates in space and time between a state in which the river planform is ordered and one in which it is chaotic. Clusters of river cutoffs tend to cause a transition between these two states and to force the system into stationary fluctuations around the critical state. Whew, that does sound exciting. What he actually goes on to say is this. If you look at a river winds and it goes like that sort of thing. Well, if you were to look at the length of the actual river and then you were to take the direct flight from one end to the other like that, and you were to find the ratio of the actual river length to the direct, that ratio is approximated by pi. Of course it is. I should throw in here a little bit of a random fact that if you look up to a rainbow, the centre of a rainbow, the angle of elevation of any rainbow is exactly 42 degrees. That can be proved by calculus. I'm not going to do it here for you because I don't know how. But that is amazing and a great fact for Hitchhiker's Guide fans. Now, speaking of pi, as I'm going to consider now this sequence. This is an infinite sequence. This means that I keep adding these terms forever. So I start with 4 on 1, I then subtract 4/3, I add 4/5, I subtract 4/7, I add 4/9, and I keep doing that forever. Now this concept of forever blows some people's minds, including my own. But guess what happens if you do that? Well, if you just take one term of that, you get the number 4. If you do the two terms, you get 4 take 1 1/3. What on earth is that? That's 2 2/3. If you do another term and you add on 4/5, you get something like 3 and a bit, and I can't work it out. But guess what happens? It goes oscillating back and forth, and it eventually settles on the number pi. That's right, that's how you can calculate pi. Just work out this sequence, or this series, to an infinite number of terms, and you have your pi. I think that's amazing, involving the number 4 and the odd numbers. But that's not all. Someone else found this out, that if we go 2 on 1 times 2 on 3 times 4 on 3 times 4 on 5 times 6 on 5 times... You can probably see where this is going. This is this time an infinite product. If we keep doing this to infinity, got the even numbers on the top and we've got the odd numbers on the bottom. What on earth does it equal? No, it's not pi. Don't be silly. It's pi on 2. Who would have thought that up? Someone did. I can't remember their name. But it gets better if you just happen to want to calculate pi squared on 6. You can do it by the following. 1 plus 1 on 2 squared plus 1 on 3 squared plus 1 on 4 squared. As long as you do it to infinity, you'll get pi squared on 6. But if pi squared on 6 doesn't float your boat, well, you can always go for pi to the power 4 on 90. And to do that, you'll need to start with 1. You'll need to add 1 on 2 to the power 4. Then you'll need to add 1 on 3 to the power 4. You'll need to add 1 on 4 to the power 4. And you'll just need to keep doing that to infinity. If you do, you'll get pi to the 4th on 90. Well, speaking of infinities, I'm now about to tell you that there are different kinds of infinities. Let's have a look here. I'll start 0, 1, 2, 3, 4. These are my counting numbers, and I could keep going forever if I had the time. Maybe one day I'll make a video and I'll do just that. But they keep going forever. How many are there? What's that? An infinite number of them. That's exactly right. There are an infinite number of counting numbers. Now let me do another number line here, and I'm just going to go between 0 and 1. Well, how many numbers are between 0 and 1? Well, I can tell you there are an infinite number of fractions because I can just keep making them up. I can go 2/3, 3/4, 4/5, 5/6, 6/7, 7/8, etc., etc. There are an infinite number of just fractions between there, but there are also irrational numbers as well. In fact, there are an infinite number of real numbers. So let me get this straight. Between 0 and 1, there are an infinite number of numbers, but between 0 and infinity, there are an infinite number of counting numbers. What this tells us that some infinities are bigger than others. The infinity here is a bigger infinity than the infinity here. And of course, speaking of infinity, one little thing that I love doing to my students is telling them that 0.9 recurring, let me just write that out for full effect, 0.9 recurring, it means we just put 9s and keep going, is exactly the same thing as 1. That's right, it equals 1. Now, before you send me hate mail and argue with me, let's just have a look at this. People are generally happy to agree that 0.3 recurring is 1/3. Okay, 0.6 recurring is 2/3. They're pretty happy with that as well. If I ask them what 0.9 recurring, they can clearly see that it's 3/3. Where it gets hazy for them is somehow 3/3 also equals 1, and that means that 1 must equal 0.9 recurring. It's not that they don't want to accept it, they just won't. And now as a special do-it-yourself exercise, I'm going to write down a sequence. If you can tell me the next number in the sequence, leave a comment by all means. The first number is 1. The second number is 11. The third number is 21. The fourth number, 1211. The fifth number, 111,221. If you know the next number, tell me. And now I want to finish this little excursus by asking, where is maths used in the real world? Because that's the question that every school kid wants to know. Well, actually not every one of them, but most of them do. In my experience, it's a question that's asked when they don't understand things. And that's okay, I get it. But I want to ask the question, who cares where it's used in the real world? What does that matter? But I'm going to give you a few answers anyway. The first thing is, prime number factorisation is used for internet security. That's right. The internet security system is based on prime numbers. Let's have a look. You should know, of course, that the prime numbers are things like 2, 3, 5, 7, 11, etc. Now, there are an infinite number of them, and by the way, Euclid provided an amazing proof which is very short. I'm not going to reproduce it here because I couldn't fit it in the space of my margin. However, thinking about prime numbers, what if I told you that I was thinking of a number and my number was 15? And I asked you to tell me the two prime numbers that multiplied together to equal 15. Well, I'm sure you'd be able to come up with the numbers 3 and 5, and you would be correct. What if I gave you a multi-hundred, perhaps thousand-digit number and said that number is the product of two prime numbers? Could you please tell me the two prime numbers? Now, I'm guessing that would probably take you to at least lunchtime. It would be impossible without sheer luck, and in fact the statistical chances of it are 0. Now that is the concept on which the internet security is based. It's based on encryption, of encrypting these numbers which are products of two prime numbers, and if somebody could come up with a way of breaking a particular number into its two prime factors very quickly, that person would crash the internet overnight, the security of it, and become very rich and famous. But it's not just about the internet security, it's about Google. What, Google? Yeah, that's right. Remember Google? That was actually the PhD mathematics project of two mathematics students. That's right. They just decided to revolutionise the world by doing a mathematics PhD. And Google is essentially a matrix. And if you want to know what a matrix is, please do not think Keanu Reeves. A matrix is a set of numbers. It's a group of numbers, and we can do wonderful things with them. Well, Google is essentially a giant matrix, and it all works by probabilities of the matrices and goes into a lot more detail than I know about, but I do know that. But now I want to ask, why should maths be useful? Is usefulness the main criteria of things in the world? Of things that matter? Of good things? I would say no way. What about a beautiful rose? How is that useful? Go and smell it and be happy. What about a sunset? Look at it. Enjoy it. It's not designed to be useful. It's pleasure. It's a gift. What about a rainbow? As you look up at your angle of elevation of 42 degrees, admire it. But don't say, how can this help me in my practical day-to-day life? It's just beautiful.